definition that's there is a definition that I just very quickly reminded you of, or mentioned yesterday, which is that we're going to start to talk about specifically the definition of a common logarithm. And a common logarithm is a logarithm with a base of 10. And what that means is, and again, I just mentioned this super quickly at the end, if I have simply the log of x, that is going to be an assumed base 10. So just have that on your radar. We're going to start, for the most part, talking about the graphs of logs, but I feel like that's a really important basic concept that needs to be on your radar. We're going to first look at the actual graph of the common log. Now, I want you to get in this habit, and men, y'all are going to be in so much trouble, and Jack Patton, as much as you're seriously so not part of it, you're about to get nailed along with the rest of them. So when it's what, I don't know exactly. I don't care.
And you know what the problem is?
No, my desk squeaked and I laughed.
Yes, you better not laugh.
Okay.
Okay, so why?
I'm gonna self-mute myself to this.
Yes, this is all going to be on a recording for people to hear. Yes.
This is.
Yeah, and then I'm going to put it on
Well,
YouTube.
in that case.
What, Jack?
Okay.
Okay, so what we're going to do is I want you to get in the habit of doing two things. First of all, we're going to graph the log, but before we do that, we're going to typically graph the exponential that goes along with it. So notice, this is an example of that. We start with the basic exponential y equals 10 to the x. I want you to get in the habit of making a really quick table from -2 to 2 of base 10. The reason that's going to be helpful is because I'm going to take this 10 to the x, and in a minute, I'm going to find the log, which we know from yesterday is the what of an exponential?
Inverse.
Inverse. So, real quickly, take 30 seconds, fill out that table. Pop your hand up when you have it done. This should be 1/100th.
110. 1.
Yeah.
10 and 100.
Come on, man.
Okay.
Nice.
And then when we create the inverse, there are several things that you gotta keep in mind that we talked about yesterday. The first is simply creating the inverse tells me I do what with my variables? I
Flip them.
and then I solve for y. Notice when it comes to a difficult question, it's the girls who
Sorry, I
answer.
didn't hear you.
Can you just
Just saying.
Wait, isn't that a bit sexist?
Well, because the actual
I think it is,
idea.
Daniel. You got it all on recording. You just nailed it right
You
now.
can't.
nailed it.
It's all. And it's going to go on YouTube. I mean, this is going to be there for everyone to know. So, Richard, when we find an inverse, we swap our variables. But it's.
I'm gonna look it up after school.
Zip it.
Alright.
We're going to always swap x and y and then solve for y.
Why can't I just?
It's the first step. But our general rule when we talk about a function is to put it in terms of y. Or I should put y in terms of x, right? So the only way, and here's the other part that you got to understand. It's not good form to keep y in an exponent. So what did we do to get y out? We created a log. So what we say is that this is my first step, but the second step says y equals log of x. Notice I'm going to put that base as the base of the log. Notice also that this is my exponential form here, and this is my logarithmic form there, right? So if you were to, I'll use the phrase apply the definition. You'll hear me say that a lot next week. Applying the definition says, hey, 10 to the y equals x. Well, that should sound good, right? Because that is the inverse of my original exponential. Now, you also know that when I go to get the ordered pairs of the inverse, what happens? My x and y switch, that's right. So my ordered pair swaps. So this is 1/100th what? -2, 1/10,
-1.
0, 1.
What are you saying?
1, 2.
10 what?
What was that?
1.
What?
Couldn't hear you.
1,
1. I can't hear what you're
She
saying.
knows she's being
100,
2.
2.
She won't cuss like usual.
Now, what am I supposed to do with this? Am I supposed to post this or not?
Yeah.
Okay.
I mean, it's just
We're gonna
going
watch
to
it. Everything's gonna
I
be
know,
so
that's really it.
Don't worry, if we call down to the office, we'll lie for you.
Okay, this is gonna get worse and worse and worse. Okay, so notice a couple things, and becomes really important. This is exponential. This is exponential what? Growth. Now notice my logarithm is also what? Growth. Slow growth, right? Because it takes 100 units to go up 2, but it's still growth. Notice in comparison to the next slide. My original, and again, I want you to get in the habit of getting the table of the exponential, in this case 1/2, the exponential graph. That's exponential what in the original picture? What exponential what? Decay, right? So real quickly, just pop your hands up when you have the table for 1/2 to the x. Okay, now this one, you should actually really sense the exponential decay as you go through those y values. -2 is what?
4.
-1?
2.
0? 1?
1/2.
1/2 and
1/4.
1/4. Again, I'm going to stress this again. Every single time you go to graph, it's going to benefit you. You don't always have to, but it's going to benefit you if you graph the original exponential with the original base first. Then, in my middle column, kind of like what we did in our notes yesterday, I find the inverse. Now, we know our ordered pairs will simply what?
Flip.
Flip. So if you want to jump to that, because that's what you see easiest, then do that. So this becomes 4, -2. 2, -1, 1, 0, 1/2, 1, and 1/4, 2. But at the same time, not only should you see that in this picture, right, where I can actually see 4, -2, right? I can actually see 1/2, 1. But I can also, how do we find the inverse? Yep, say louder. Flip x and y. So this is x equals 1/2 or 0.5 to the y. But then I always have to solve for y. So I turn it into the definition of log, right? Which says that this is the same as y equals, can you give it to me?
Log 5x.
Very good. What I want you to be able to do before you leave today, first of all, is answer this question. What is the inverse of a logarithmic function? You should say what immediately?
Exponential.
An exponential. Jot that down. Now, give people a chance to think on this. How do you know? How do you know? How do you know an exponential? There's a couple ways, yeah.
Somebody just come up with a...
No joke, that's actually part of it, right? Someone, and you have to understand this about logs, which I think is unique. Someone created a logarithm, right? Actually physically said, hey, we're going to define a function so that. So that what? It's the inverse of an exponential. The 2 other reasons I would say, what are they? Once you get into the nitty-gritty of the actual function. The x's and y's what? And the graphs what?
The question about EX or YX.
Yeah, they reflect about the line y equals x. Now, on the next slide, one of the things I want you to be really comfortable with is knowing the difference between the domain and range of an exponential compared to a logarithm. We're going to talk about original points. I'll talk about what that means, and then what happens to the asymptotes. We actually did this yesterday. It's in your notes, but I want you to kind of, if you need to, go back and forth between the front page. But we want to really know this. So, for example, what I want you to really know is the domain of all exponentials is?
-50.
Yeah, all reals. Now, don't miss this. Literally, by saying this, what have you just also stated? Very good. The range of a logarithm. Now, yes, when we talk about the range of an exponential, he actually said it in a decent way. Did you hear what Jake said? Yeah, that's actually nothing mathematical, but he kind of made up his own notation. It's from the asymptote to infinity. What is that? Okay, what did he also therefore just state?
The domain
Of
of the logarithm.
Of the logarithm.
Of the form
Y equals log BX.
See, I wrote down 0 on my page.
Okay,
Hey.
so notice, and don't miss this part, if this is exponential growth, this logarithm is exponential growth, even if I change to exponential decay, right? The domain and range are the same. They still swap for the log, although the log will become what? You saw this on the other picture. It's going to become decay, right? And it's not technically referred to as decay. We would just say it's a decreasing function. But just as decay is decreasing, my logarithm will also be decreasing. Now, in both cases, exponential growth or decay, what will they, no matter what the base, what will they automatically go through? 0, 1. Why?
Because
Anything
exponent to the first.
Anything to the 0 with power is 1. Now, you should immediately be able to tell me what's on every logarithm graph.
One,
What is-
zero.
Why? Because
It's
the
the
inverse.
yes.
Oh.
I'm glad. Actually, I almost am glad we're recording this. Like, how you can't make this up. This like wildness.
No, it's like the best classroom ever. You know?
So exciting.
Hey,
Hey,
Jake, stop touching
what's-
the lights.
That's funny.
X
Um,
is
That's
0.
what happens every
Yes,
time.
y equals 0 is my.
Wasn't even-
Now listen to this. Horizontal asymptote of my exponential. And when I think about this, it becomes what in a log? Now, I'm going to point out a couple things about this. First of all, that should make sense because it reflects, right? Horizontal becomes vertical. Also, keep in mind when we're in this form, what is that locking me into? I cannot take the log of a, yes, of a negative number. If I just, now this is seen in multiple places. It's first seen in the asymptote. It's also seen in the domain, right? Why? Because the outputs of an original exponential can never be negative. Now, once you shift it, of course, obviously it can move, right? But as an original, I have no exponent that I can plug in that will cause a negative number. Really listen to that. And I'm going to say it again, and I want you to nod when you totally follow me. I can, if my inputs are x's, no matter what I plug in here, there is nothing I can plug in that will cause a number to become negative. Everyone with me? So when you reverse that idea, if we're saying no outputs can be negative on the exponential, then on the log, no, say it,
Base.
inputs can be negative, right? Okay, now, what we need to focus on now is this idea of graphing logs, okay? So what I've done here is we're just going to start, and I'm going to teach you a process. Like, okay, if I give you a log graph, what do you think about? So, just based on what I've said so far, before you ever try to graph a log, before I ever try to graph a log, what am I going to suggest always that you try to do first?
Put the exponential in
The exponential. What is the exponential that corresponds to y equals log base 3 of x?
Y equals 3 RX.
Y equals 3 to the x. So what I want you to get in the habit of doing is, not because I'll always say graph the exponential first, but because it's very helpful to understand what my ordered pairs are in a log if I've first considered the exponential. I'm going to run my exponential from -2 to 2. Pop your hand up if you can quickly give me those values. Who's got it?
1, 9,
Go.
1/3, 1, 3, 9.
Okay. Now, the reason this is helpful is what? Why does this matter in regards to the log graph?
Flip, it's just flip.
That's right. I'm just going to flip them, right? So when I go to do my inverse, I've already graphed it here for you, but you want to understand, hey, if I think about the exponential, what corresponds to it as an inverse is the reverse ordered pairs. The x's and y's flop, so now I have 1/9 -2, 1/3 -1, 1,
0.
0. Now, a couple things that I want you to notice here. I want you to see that my outputs are really what? Give me a different word. A logarithm is an exponent. Say that phrase again. A logarithm is an exponent. So what happens in my logs, because over time you're going to get away from this, from the exponential, what happens is you got to start to understand that my inputs are powers of 3. Do you see that? What would be a logical next one to list?
27.
Yes, 27 what?
3.
3. If you're really good at your powers of 3, what's next? 81,
81.
4. So notice your inputs now are your powers of 3, and your outputs are the exponents that are those powers. So, you ready? Got it? This is what's going to happen. We're going to start to shift and move. But before we do that, we got to just be able to graph a log. So, with someone right around you, take a minute and do it. Sketch a graph. If I give you, hey, graph log base 4 of x, what am I going to suggest you do first?
You do the
Y
right.
equals 4 to the x.
Okay, do it.
Oh.
So graph y equals 4 to the x, sketch that with a dotted line, then get the points for log base 4 of x, and then graph the log. Go. Okay, so in the next 10 seconds or so, just glance up here.
Accurate. Jake's distracted.
Okay, now your graph is hopefully more detailed than mine, but what I want you to notice is my quick growth, exponential growth for y equals 4 to the x is here on the table in red, on the graph in black, yes?
Yep.
Okay. Then we go and we want to find the inverse. I'm going to swap my points, right? And as I do, what you have to get in the habit of noting is this horizontal asymptote then becomes a vertical asymptote on the log. I have a point at 1, 0. 4, 1, 16, 2 is all the way down here. I've got that.
Oh, crap.
Okay. Makes sense, yeah? We are going to now take this idea and begin shifting and stretching. So, when you look at, now look, this is the graph we just did, right? We just took, in the above graph, log base 4 of x. And we're going to now shift it. How much?
3 to the right.
3 to the right and
4 up.
4 up. Got it? 3 to the right and 4 up. Now, what I'm going to do, so for me, it's going to look like this. I'm going to go back to the top slide, and I know that these are my inverse points, so I am going to try to copy and paste these. So I want you,
If you click
Click
shift,
all of them.
if you click shift and then click on
Shift
the rest
click.
of them.
Shift click.
You click
Shift.
shift down and then you just click all of them. Yeah.
like that.
There we go.
Come on. So I want you, while I copy and paste this table, although it might take less time just to do it myself, will you copy and paste that table on your next slide?
Yeah.
Copy this side.
Then go to object.
Then you go copy and paste.
Oh, wait, that's.
Copy.
Oh, wow.
Then you guys copy.
Man, see.
I got it.
I go to the bathroom now.
Thank you.
No,
Man, why?
but you can in a minute.
There it is.
We talked about last time. And it's been like 20 minutes.
I know, I'm comfortable with it, though.
Wait,
But I do appreciate you keeping track of that, Jake. Thanks.
My bladder's not comfortable with it.
All right, well, can you keep maybe your bladder issues to yourself a little?
I use restroom.
No.
I use the restroom.
Still no.
Anyone got a water bottle?
Okay, did you repeat that? You're gross. Did you repeat that table? Yeah? Okay, so now what I want you to think about is we are going to take this table and we're going to do to it what was said out loud. You should look at this and say, okay, this is shifting right 3 and up 4. Okay, now I want you to go ahead and sketch the log, the original. And again, notice that at first we always sketch the exponential followed by the log. On the shifts, we're going to sketch the original log and then the shift. Caroline's giving me a look like, I have no idea what you just said. We're going to sketch the original log that you just did up above. So there's 1, 0, 4, 1, 16 2's way out here. I've got this picture, right? And now we're going to shift literally the way you said. So what I mean by that is, I'll use the y's first to give you an idea. What did you tell me to do to all the y's?
You add them by 4.
You literally physically add 4 to all of them. So -2 plus 4 is?
2.
-1 plus 4 is?
3.
3. This is 4, then 5, then 6. The next piece is we got to move all of my x's 3 to the right, which is physically adding 3. So it's okay if we write 3 and 1/16, 3 and 1/4. This is 4, 7, and 19. Now, what's going to happen though, which I also want you to get in the habit of doing, is clarifying, just like when I move the exponential vertically, my horizontal asymptote shifts. If I move this horizontally, my asymptote shifts. The original asymptote here was at x equals 0.
Now it's 3.
Now it's at x equals 3. So what I like to do when I start to shift these is actually redraw. Listen, is redraw my new asymptote. So I'm going to go, okay, here's 1, 2, 3 over. Here is my asymptote. Now, for those of you who really follow this, has there been any scale change at all? No. So the same physical pattern of going over 4, up 1 from the asymptote, who sees what I mean by that on the original? We do the same thing now. So it's like a check along the way. So pretend for a second I didn't have this table. I could go to 3 and I could count over. 1, 2, 3, 4, up 1. Right? I originally went over 1 and hung on to that x-intercept. Go from the asymptote. Go over and cling onto that x-intercept. Now, here's the point. Notice I didn't use the table. Do you see what I mean? Who sees totally what I mean about moving over the same amount of space? So we'll see how from the asymptote to the point you went like 1 unit. You see what I mean? So when I have my new asymptote, I go over 1 unit. What I love about this, it's like having self-checks built in. So when I look at my table, which I haven't glanced at, I should have an ordered pair at 4, 0.
Wait.
Do I?
No,
Are you supposed to go at 4?
4. Okay, so what have I not done yet?
Gone up 4.
Now I got to go up to 4, right? So I go here, and my final graph will be here in blue. I'm going to go 1, 2, 3, 4. But the beauty of it is, this was up 1. I'm going to go up 4 more. 1, 2, 3, 4, up to here. So now I can see, okay, well, this is at 4, 4, right? This is at 7, 5. You see what I mean about being built in?
Yeah.
It's like, if you never understood the table a day in your life, you can still graph it. Make sense? Okay. Does it really make sense?
Yeah.
I can't totally tell.
Okay.
Okay. Well, Daniel, you're not the only one, so I'm checking with a couple other people too. Yeah, Nick.
I just use it over the points on the table.
Yes. Oh, yeah. You can, and as long as you understand, getting the table is totally fine.
Yeah.
Okay. So with someone right around you, all I want you to do on this next slide, I want you to name the original log, and then I want you to name what happens to the graph. It'll take you like 2 minutes. Go.
Well, the graph goes 2 to the
You don't
right.
need to shout it. Just share with someone right around you. Go ahead.
2 to the right,
Goes
right?
to the right.
No, it's not 2 to the right, people, just so you know.
No.
Two.
Two down.
Yes.
Two down. Come on, guys. Come on, Jake. The next one's 2 to the right. Guys, let's make it.
And we got one to the left. But
You have to put down the log.
Jake, be quiet now.
We're going to on the next slide.
Did you end the video?
Not yet. I know. You're tempted to do something else, aren't you? You're like, I got a few more minutes.
I was gonna yell. Ah, tile mass.
Hey, if you have something filled out for each of these, will you raise your hand? Okay, ready? Pop your hand up. What do you do for A? Ella, go. Down 2. B. And Nick.
Two to the right.
2 to the right. C. Be careful there, Richard.
Oh, wait.
One
left.
left.
5 down.
5 down. Last one, D. Jake.
4 to the right.
Okay, so on the last slide, all we're going to do is graph these. So the majority of your homework that's due on Monday is going to be to practice. So we're going to do one more together, and then the rest, I'll just going to give you time to work. So if I asked you to graph A, we said, okay, that first one is 2 down, right? So I'm going to take my original log, which is log base 3. Now, we actually already made that table. My suggestion is always to write out the original log. And -2, -1, 0, 1, 2. Real quickly rattle that off. You ready? The original is I shouldn't say that. That's my exponential.
What's going on?
Yeah, sorry.
3, 9.
Yeah, it's 1/9. My bad. So this is 1/9, 1/3, 1, 3, 9, with my exponents being -2, -1, 0, 1, 2. We're going to now move all of those what?
2 left.
2, try again, 2 down. So do I do anything with my x values? No. My x values don't change, and my part A physically goes down for all my y values, so -2 becomes -4, -1 becomes 0 becomes -2, 1, -1, 2 becomes 0. All of my x values are the same. What I really love about this is, if you sketch the original, I think you can physically see everything move. So I had this original asymptote at x equals 0. I've got 3, 1, 2, 3, 1, 9, 2. I'm going to sketch it in dashed points. And now, again, we've set it. We've set it moves 2 down. We've got ordered pairs that have moved 2 down. And now when we draw it, we should see it. So when I graph 9, 0, for instance, I can immediately see, oh, there, whole thing is moved 2 down. 3, -1, oh, there, whole thing is moved down. This goes like this. Quick question, has my vertical asymptote changed? No, it has stayed the same. Okay, now, what we're going to do, because I'm going to stop the video here, you're going to do the next 3, and we might get done early, so if we do, then you can transition into your Form K, but I don't want you to do Form K. You're going to do all of Form K for the weekend, so that I can turn this video off. Give me your eyes real quick. We're going to spend the next 5 minutes graphing the remaining 3, okay? Your homework is Form K. It's due on Monday, okay? When you walk in the door on Monday, this is what you need to have. Your 7.1 and 7.2 worksheets, which I have not checked yet. You have 2 now, we have a Form G and a Form K from Section 7.3. and you should have your circle worksheet, your packet. If you know what all three of those are, will you raise nod so I know we're okay? Okay. Your assignment, you're going to have time, when you're done with the STAR test tomorrow, you're going to have time to work, right? So just make sure that everything is done when you walk in the door on Monday. I'm going to do something on Monday. We are going to have a quiz. Look right here. We're going to have a quiz on 7-1 to 7-3 on Tuesday. Everyone with me? Okay. I'm going to stop the video. I want you to do these next three, and then I'll take questions at the end.
Ah, Felicia.
What's Felicia?
May wonders never
This man-
cease.
This man